Let's get ready to do some math. All right, related rates, day 2. How you doing out there? Pre-calculus honors. Hope you took a look at your homework. We'll start right there. Remember related rates, okay? They're going to describe some kind of situation where, one thing is changing with respect to time, and related to that, another thing is changing with respect to time. They actually give you the rate at which those two things are changing at a specific instant. They'll give you one rate, they'll ask for the other rate at a specific instant of time, which many times is just telling you how long a measurement is, but not always, okay? We'll talk about that as we get to more complicated types of problems. Here, hopefully, your first homework problem, whichever one this was right there, I can't read it, but I know it's on your ditto anyway. So whichever one this was, I forget, I don't have the stuff in front of me. Hopefully not too bad. I think they gave you the situation where I can't read it, it's cut off, but I think this is when you threw the pebble into the lake and it's, the ripple is increasing in concentric circles. It just means the circle that's getting bigger and bigger. They tell you the rate at which the radius is increasing. Remember, when you write down a generic rate of change, you got to indicate whether it's positive or negative. If something's getting bigger, it's positive. Something getting smaller, the rate of change is negative. More on that today. And then we want this rate, the rate at which the area is changing at a given instant. They said when the radius is 4. Get that formula that relates to the variables. Differentiate implicitly with respect to t. Then you could actually plug in to solve. Remember those units. If it's an area that's changing square feet per second. The spherical balloon right here also very, similar to the one we did in yesterday's video, only here you had to actually end up solving for dr over dt. It wasn't already isolated. Let's do a practice problem real quick. Let's try number 12 from the packet. And here they're talking about a circular plate of metal is heated in an oven. Pizza. Do you want a pizza? Hey, do you want a pizza? This is pizza right here, okay? Well, that's what I think about when I think about a circular plate of metal is heated in an oven. And what is Science 101? When you heat metal, what does it do? Much like what my waistline does pretty much every day, but more on the holidays, expands, okay? So here, circular plate of metal is heated in an oven. Its radius increases at a rate of 0.01 centimeters per minute. I smell a rate. Do you guys smell a rate? I think they gave us a rate. And at what rate? They want a rate. Is the plate's area increasing? I hope they indicated a specific instant. They did when the radius is 50 centimeters. So once again, drawing a diagram here, the circular plate of metal pizza, the diagram probably seems useless to you at this point in time because everything's always changing with a circle and a sphere. That's going to change today when we get to the right triangle. So it will be a little bit different, but we know that there's only one linear measurement for a circle. It's the radius, and there's no way that radius is ever remaining constant if the size of the circle is not remaining constant. They actually tell you the rate at which the radius increases. That's dr over dt, or dir over d, if you want to pronounce it. So the rate at which the radius is changing with respect to time, it's a positive rate of change because the radius is getting bigger. If it was de-expanding, condensing, however you say that, then you put a negative right there for the rate of change. More on that today. They want the rate at which the plate's area is increasing, so they want dA over dt, the rate at which the area is increasing with respect to time, or really the rate at which the area is changing with respect to time, and the specific instant. They said when the radius is equal to 50 centimeters. And don't be the person who just, labels the radius to be 50. The diagram that you draw always has to be in flux, okay? It's got a diagram that works at any time t. So r is not 50 at any time t. So maybe write that down. Diagram must represent any time t. Must represent any time t. And you can quote me. All right, so look, let's get a formula that relates to the variables. There better be an A in it, where A represents the area of a circle. There better be an R in it, where R represents the radius of a circle. Also a pirate's favorite letter. Anyway, that's going to be the area formula. Area equals pi r squared. You guys know why pirates like to say R, right? They're on a boat one day, the captain's looking at his number one. The number one looks up and he sees ships on the horizon. He's like, Captain, there be ships out there. And the captain's like, arr, arr ships, trying to correct his grammar. Anyway, let's take the derivative implicitly with respect to t. The derivative A with respect to t is dA over dt. Equal to, drop the 2 down. 2 times pi is 2 pi. Raise r to the 1 less. Multiply by dr over dt. Here's what I want, dA over dt. 2 pi is constant, but now I'm taking the derivative implicitly with respect to time. I'm looking at one instantaneous moment. What instantaneous moment are you looking at, Mr. Berto? That's a great question, Rourke. The instantaneous moment I'm looking at is the instantaneous moment, and the radius is 50. So I label the R with a 50 right there. And then the dr over dt, put 0.01. That's dA over dt. You can still do this without a calculator. People complain. It's a take home for this, obviously, just like everything else now because of the quarantine. You'll have a calculator for it, but I normally give people the calculator for this take home right here. 0.01, what is that, 1/100th? Right, so if we actually write it that way, it's a lot easier to now actually say, hey, the 50 and the 100, divide both by 50. And then look, the 2, you could divide the 2's by 2, top and bottom, and you're just left with pi. So dA over dt equal to pi. Units! I need units! And think about it, this is an area that's changing with respect to time. Area is not measured in centimeters, area is measured in square centimeters. And since it's with respect to time, per minute. Like I said, you could roll the units into the calculation if you want to. It's really up to you. Who is it up to? All right, so, moving on here. Let's get some formulas going. Formulas continued. You should have these notes from yesterday. Now it's formulas continued for today. And now let's talk about my favorite shape for these types of problems. If you Google related rates online, that's probably the first type of problem you'll see. The right triangle. And we spoke about that yesterday with Shalene trying to, Shalene Dion, trying to actually hang those, Christmas lights that we were talking about. Usually I purposely call on a student who's Jewish just to play around and have fun in class, but this is videos. I'm trying to make the best of it. Right triangle over here. Right triangle, there's actually a lot of different sides that could be in flux, but there's also sides that could be constant, right? If the ladder's leaning up against the side of a house and starts to slide down, these distances get bigger, but the hypotenuse remains the same. But there are situations, maybe you have a car start here and another car start there. One goes north, one goes east, and they're moving, and the distance between them is also moving. So sometimes you could have this be 3 variables, sometimes just 2 variables. Impossible to have just one. So I'll call this A, B, and C for the sides. And look, believe it or not, the most important formula you could use to relate the 3 sides of a right triangle, A squared plus B squared equals C squared. And it's lovely because even though the left-hand side is multivariable, there's 2 variables, they're connected by addition, and we could break up derivatives over addition or subtraction. The problem is if you want area of a right triangle, remember, a right triangle, the 2 legs will always form a right angle. So no matter how this thing is oriented, you could always say one leg is the base and one leg is the height, no matter what. So you could really, for the area of a right triangle, say 1/2 leg times leg. In this case, 1/2 A times B. And this gets a little finicky over here because the A and B, excuse me, the A and B are connected by multiplication. Thus, if you wanted to differentiation the right-hand side, product rule, product rule, product rule, product rule. But we won't see that for a day or 2, okay? So anyway, let's actually dive in and have some fun. And let's go back to that packet right there. And let's talk about number 1. 1 rhymes with fun. And that's what this lesson is. That's what every lesson is in our virtual math classroom. A 5-foot ladder, it's a ladder that I'm taller than, leaning against a wall, slips. Now things are getting interesting. So its base moves away from the wall at a rate of 2 feet per second. Gee willikers, Batman, that's a rate. How fast will the top of the ladder be moving down the wall? That's another rate. I hope they gave us a specific instant when the base is 4 feet from the wall. So that's how you know it's a related rate problem. They gave you a rate, they asked for a rate, a specific instant. Let's draw a diagram. And you can really have a lot of fun with it, right? Here you have the wall, here you have the floor. The floor is the wall or the ground, whatever it happens to be. And then when you draw the ladder, you have some fun, get into it, okay? But really, you could just draw a right triangle because that's what's going on. But you got to think about what sides are variable and what sides are not variable. You got to understand that as the ladder, slips, they tell you that the base moves away from the wall at a rate of 2 feet per second. That means this distance is getting bigger. And if that distance is getting bigger, you have to label it with a variable. You could use any variable you want. A lot of people use B for base. That's pretty good. You could use X. We'll use X right here because it represents a horizontal distance. Horizontal distance, a lot of time we'll use X. Not always. But the important thing is they tell you the rate at which X is changing with respect to time. Since X is getting bigger, I know the rate of change is positive, and the rate at which it's getting bigger is 2 feet per second. But remember, while this is happening, there's another rate that's related to this, and that's the rate at which this guy right here is actually getting smaller, okay? So look, he's not remaining constant, he's getting smaller. We gotta label him with a variable. H is great for height of the triangle. Y is good too for vertical distance. We don't know what y is equal to. We don't know dy over dt either. They want to know how fast the top of the ladder is moving down the wall. That's how fast this distance is getting smaller. They actually want dy over dt. Then they tell you a specific instant when the base is 4 feet from the wall. Here's the base of the ladder. Here's the wall. That's when x equals 4 feet. Don't be putting when y equals 4 feet. You got to think about it. Okay, this is not the base. This is the top of the ladder. If they said when the top of the ladder is 4 feet from the base of the wall, well, then you could say when y is equal to 4, be careful. And how about this? 5-foot ladder. As this goes on, as this thing slides down, is it going to change? No, it's going to remain constant. So this diagram works at any time t. The hypotenuse is always 5, but the legs are always variable if you're talking about every time t right there. So be careful with something like that. Some people say, hey, maybe this is an extension ladder. Maybe as it slipped down the wall, it actually started to condense and collapse a little bit. Yeah, that's just a multivariable type of problem that we can't handle right now. But eventually you do stuff like that. Not in this class. So here, let's get a formula that relates the variables. It better have a y in it, where y represents this distance right here. Better have an x in it. I go with Pythagorean theorem here. I mean, come on. We know x squared plus y squared equals 5 squared. Don't be putting 4 squared plus y squared equals 5 squared. The formula, just like the diagram, needs to work at any time t. Needs to work for any time t. So make sure anything that's variable is represented by a variable in your formula. Anything that's constant, represented by a constant. You could actually make the 5 equal like c, something like that. We'll talk about that in a minute, actually. Let's do this first. Let's differentiate both sides implicitly with respect to t. I'm loving the right-hand side. Addition. I know the derivative of x squared with respect to t is 2x. Then put a dx over dt next to it. Plus the derivative of y squared with respect to t. Drop the 2 down, rewrite the y, raise it to the 1 less. Now multiply by dy over dt. You can see multiple rates are showing up, but that's all right. By the way, the derivative of 5 squared is not, drop the 2 down, 25, or 2 times 5 is 10. No, 5 squared is 25. That's a constant. The derivative equal to Mr. Pushy's IQ. We know these things, Zeto. All right, so look, this right here, and by the way, over here, some people do say this is a c instead, of 5. They say c squared. Then they take the derivative. They get 2c dc over dt. But remember, 5 is not changing. It's remaining constant the length of the ladder. So if something's remaining constant, that means its rate of change is equal to 0. And 2c times 0 would still be equal to 0. You don't need to do it that way, but you could do it that way if you want to. You could start plugging things in right now. And look, I know you have a calculator, but be smart. You could divide by 2 on both sides here. Why would I do that? Because then I could split the division, cancel out these 2's over here. 0 divided by 2 is still 0. So I get x dx over dt plus y dy over dt equal to 0. Even with a calculator, do stuff like this. Simplify your work. It's going to make things easier in the long run. Trust me. And look, the dy over dt, that's what I want. No, 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 no. That's what I want. So let's replace everything but him. I've stopped time. At what time is this? It's the instant when x is 4 feet. Booyah. Let's put him right there. Dx over dt I know is equal to 2 plus y. I don't know what y is. I also don't know what dy over dt is, but that's okay, because dy over dt is what I actually want to solve for. So people are like, how am I supposed to get what y is equal to? Think about it. Higher order thinking question of the day. How can we figure out what y is at this particular instant? Pause the video and think about it. And we're back, okay? And look, this is the instant when x is equal to 4 feet. The diagram is no longer in flux. So think about what it's going to look like at the instantaneous moment when x is equal to 4 feet. Well, the ladder is still always equal to 5 feet, right? And that means y must be equal to 3 feet. Okay, you should know about the 3, 4, 5 Pythagorean triple. If you really want to know where it comes from, you could just do 4 squared plus y squared equals 5 squared, and you'll get y equals 3 that way. So sometimes when there's not just one linear measurement that's changing, you got to go back and think at a specific instant, what is another linear measurement equal to? I know y is equal to 3 in this particular instant. Kind of cool, right? Subtract the 8 from both sides. 3 dy over dt is equal to negative 8. Divide by 3. I get that dy over dt is equal to negative 8 thirds. Units. I need units. but it's y that's changing with respect to time. Y is just a linear measurement. So if x, the other linear measurement, was in feet per second, that means y is also going to be in feet per second. Look, if it was an area changing, it'd be square feet per second. If it was volume changing, it'd be cubic feet per second. Pretty much just anything else, any linear measurement changing, just going to be feet per second. There's a lot of stuff going. Negative. Why would it be negative? Oh, because y is getting smaller. And if something is getting smaller, that means that its rate of change is actually negative. So that's kind of cool. Just be careful. They want to know how fast the top of the ladder is moving down the wall. How fast is indicative of speed. So if you want to know how fast, that means you're looking for speed. Okay, and that means this is actually velocity. It actually tells you the rate at which y is changing, and it tells you the direction as well. How fast is speed? That's the absolute value of velocity. So that'd be 8/3 feet per second. Which you don't see a whole heck of a lot. You'll see it in a bunch of problems we start with because they're textbook types of problems. And a lot of times they just want to know how fast, because in a real world situation, people can relate to that. Usually on the EP, they'll actually just ask, what's the rate? At what rate is the distance between the top of the ladder and the bottom of the wall changing? And if they want to just know a generic rate of change, that means you have to tell them whether it's a positive rate of change or a negative rate of change. So you'd actually want the negative in that particular case. But if you want to know how fast, it's always positive. More on that when we do the next problem, number 6. 6 rhymes with candlesticks, and that's what Jack jumped over. A little risky if you ask me. A boat, it's my boat, is pulled into a dock by means of a rope with one end attached to a bow of the boat. Okay, the bow of the boat, what is that, the front of the boat? And the back of the boat is the stern. I'm not a big, boating guy over here, but I know that port is left and starboard is right. Yeah, whatever. One end attached to the bow of the boat, the other end passing through a ring. You better put a ring on it. Attached to the dock at a point 12 feet higher than the bow of the boat. A lot of words. If the rope is pulled in at a rate of 4 feet per second, I smell a rate. You guys smell a rate? How fast is the boat approaching the dock? How fast they want a rate is the boat approaching the dock when 13 feet of rope is out. This is a related rate situation. The hardest situation here is actually drawing the picture. Okay, you have your water over here. Then you got the dock. What's up, Doc? I think I'm funny. Okay, and if you draw a boat, maybe back here. I'm an astounding artist over here. It's my boat, okay? And they actually say that it's being pulled in to the dock through one end attached to the bow of the boat, a rope, and then another end on a ring on the dock right here. Right, so it's looking a little something like that. And then if you think about it, they tell you that this ring is attached to the dock at a point 12 feet higher than the bow of the boat. So here's the bow of the boat if you go straight out over here. And then if you head upward, we know this distance right here is going to be 12 feet. It's actually always going to be 12 feet. As the rope is pulled in, this distance will get shorter. This distance will get shorter, but this distance will always be 12 feet. I know it doesn't make sense. It's just if you have extraordinarily calm seas, this distance will always be 12. Really, the distance is going to be oscillating, right? Changing as the boat, bobs up and down. So really, if you want to do that type of situation, you need to define a function just to talk about this height, some periodic function that oscillates. You'd probably use a trig function for it. That's way beyond our pay grade in here. We don't talk about that. These are the simplest types of situations. So we'll say that this is 12, but this is not variable, but this is variable. The length of rope, we know it's getting shorter. I'll call it R for rope. And we know this distance is also getting smaller. I'll call it X just because it's a horizontal distance. And they tell you the rate at which the rope is pulled in. So that's the rate at which R is changing with respect to time. That's dr over dt. They tell you it's 4 feet per second. And if you write this, it's not horrible, but it's wrong. Okay, why is it wrong? Because this right here is a generic rate of change. The rate at which R is changing as time goes on, and R is getting smaller. And if something is getting smaller, its rate of change is negative. And that's important because that could really affect your answer, making it the opposite of what it actually needs to be, or really just throw it into even more flux with more complicated types of problems. But when you write a generic rate of change down, it is understood that you need to indicate whether it's a positive rate of change or a negative rate of change. People they didn't say -4 over here. They said the rope is pulled in at a rate of 4 feet per second. Yeah, but because they use the phrase pulled in, By context, they're actually letting you know that the rope is getting smaller. There's no context here. This is generic mathematics. Y'all's got to indicate that's a negative rate of change. A lot of people flub that up, by the way, so be careful. What do we want? What do you want from me? We want to know how fast the boat is approaching the dock. That's going to be the rate at which distance is getting smaller, so we want dx over dt. When, and the specific instant is when 13 feet of rope are out. R represents the length of rope, so R equals 13 feet. People are like, oh, when X equals 13 feet. Yeah, that makes sense, right? When you attach a rope, it just juts out of the boat horizontally and floats there. No, this is the rope right there. Have some common sense. Think about these things. Most of you equipped to handle things like this. Some of you struggle. Ian, Hadrian, he struggles with these problems a lot. But, the rest of you should be pretty good. Now we want to come up with an equation that relates to variables. There should be an X in it. There should be an R in it. I'm thinking Pythagorean theorem. Make sure you set it up right. People are like, oh, x squared plus r squared equals 12 squared. I know what I'm doing. No, you don't, okay? X squared plus 12 squared equals r squared. Sorry to actually expect you to recall 8th grade mathematics, but here we are. Now I can differentiate implicitly with respect to t. I know the derivative of x squared with respect to t is 2x dx over dt. Plus, the derivative of 12 squared is the derivative of 144. That's 0, y'all, equals the derivative of r squared, 2r dr over dt. And if I were you, I'd divide by 2 on either side. And really, we just get x dx over dt equal to r dir over d. That's dr over dt. And that's what I want, the dx over dt, right? So everything has to go. The x has to go. The dx over t, you could stay. You're what we want. Thank you. The r's got to go. The dr over dt's got to go. I know this is a specific instant when r is 13. I know it's a specific instant when dr over dt is -4. You might have a +4. Then you end up with an incorrect answer, even though it'll be closer than you think. And then x. Oh, yeah, what's x at this specific instant? Well, we've just stopped time. A la Dr. Strange, okay? What does this look like when you stop time? Well, we know that 12 is always 12. He's a constant. R is this distance up here. It's 13. How do we get what x is equal to? Pythagorean theorem, x squared plus 12 squared equals 13 squared. Or maybe you're just good enough to know about the 5, 12, 13 Pythagorean triple. Pretty famous one. Everybody knows about the 3, 4, 5. And also, you could dilate this. So 6, 8, 10 is a popular one, but it's just a 3, 4, 5 dilated by 2. So you really just need to worry about 3, 4, 5. The 5, 12, 13, very, very popular. Okay, how about the, is it 5, 18, 17? I think it's 5, 18, 17. Why can't I remember these things right here? I'm just taking out my trusty, hopefully not too dusty, graphing calculator. 5, what did I say, 5, 17, 18? I don't know, it just doesn't sound right. But let's see, is that equal to 18 squared? No, it's not, but it's close. Why can't I remember the other one? 4, 17, 18? Nah, it doesn't sound right either. Anyway, well, sorry, I can't recall that one off the top of my head right now. Oh, the 15, 17, 6, I don't know what it is, all right? Anyway, there's actually a famous rock, believe it or not, that was unearthed years ago, many years ago, called Plimpton. I think it's 332, 322, 322, I think it is. Yeah. And this rock actually had a list of a bunch of Pythagorean triples, okay, from an ancient civilization. So it's really cool history of mathematics if you actually take a look at things like that. I actually used to be in a punk rock band back in the day. My punk rock band was called Porcelain Decay. I've mentioned that to you before. But there was another band we used to play with who was called Plimpton 32. And one day, after they played, I go up to them. I'm like, dude, are you guys named after that rock that has the list of all those Pythagorean triples? And they looked at me, wow, you're the only one who's ever come up with to us and actually, knew that right there. So Connor right now is calling me a nerd, but that's cool. That's kind of interesting, okay? I'm still just really trying to stall for time so I could figure out what that other Pythagorean triple is, but for some reason I can't figure it out. Maybe it'll come back a little bit later in the lesson. So anyway, x is 5 over here, so that means that dx over dt, if we do 13 times 4, what is that? 40 plus 12, so that's going to be 52, but negative 52 fifths. Units, I need units, right? Divide by 5 on both sides. My units, this is a linear distance that's changing. It's going to be in feet per second. But make sure you answer the problem appropriately. It makes sense that dx over dt would be negative because you could see that x is actually getting smaller. But here they actually want to know how fast the boat is approaching the dock. So remember, if you want to know how fast, you actually want the absolute value. So that's just really going to give us 52 over 5 feet per second. Even though in the AP exam, you'll see on my test that I eventually get out to you, I'm more interested in the negative 52 over 5 than I am in the 52 over 5, okay? So just something to think about. Was it 6, 17, 18 for that Pythagorean triple? I'm still trying to think about it here. 18 squared. No, but it's really close. I don't understand why I can't figure it out. Anyway, just try to remember, okay, that when a rate of change is, negative, that corresponds to when a distance is actually getting smaller. So be careful with the way you set up these formulas. And the Pythagorean theorem, the right triangle, multiple linear measurements that could be changing. So you might have to figure out at one instantaneous moment what's actually, the distance at one specific moment. We need to know what x was equal to. So kind of one extra step, hopefully not too terrible. That's related rates day 2 right there. We'll get in some more interesting stuff tomorrow, which I believe is Thursday. And you will have a take home at some point in time as well. So I hope everybody is doing well. I'm sorry I couldn't figure out that other Pythagorean triple. It's really bothering me. 15, 17, 6, 15, 17. Does that make sense right there? No, that's not it either. Whatever. I can't figure it out. So we'll talk about it another time. And this is Berto being frustrated he can't remember Pythagorean triple, and I'm signing off. Adios, y'all.